like to return to the example we were looking at last time, okay, which was basically trying to get a sense for how this weird old CPU runs. And let's re-go through the example, but I need to make a slight tweak to it. Oh, wrong keyboard. Okay, one moment, please. I need to put some R's here. So I remembered that I redefined some of the syntax. And then let me typeset it and it'll show up here. Oop, and I need to do R's here and here too. Okay, so I've been kind of editing the syntax for stuff for the last, few years, and have kind of am starting to coalesce on something a little bit more, um, uh, well, both a little bit more, well, a little simplified, but also um, something that looks maybe a little bit truly like a real assembly language for a real processor. Um, so that those of you guys who are going to go on and take, where are the freshmen that want to take a bunch more computer science, right? Okay, so next semester you'll take CS111, which will be a full course on Python. And then the semester after that, amongst other things, you could take CS241, which is an entire class on machine organization. So the sort of the couple weeks that we're going to spend on that, just blown up to a full semester. Okay, so what was the point of this program in English, right? Well, let's load one register with the number 1, another register, say, with the number 2, and then add the two things together and put the answer someplace, and then store that out to memory, right? That's all this thing does. It takes 5 instructions, essentially, to do addition, okay? Because you've got to get the two numbers that you want to add into places where you can deal with them. Then you actually add them, and then you need to put that result someplace, okay, memory or whatever. And then the last instruction is maybe not really an instruction. It just says, well, we're finished, so we can stop executing code at this point. We can halt. Okay, so got that. And we looked at, so let's go to our simulator here. Let me copy the link. Where is Safari? Here it is, okay. With the machine code loaded in. So just so that we're clear on the distinction here, right, there's sort of different levels at which we could program. We could write instructions in English, which is maybe in some sense the highest level of programming that you can do because it's the most machine readable, or sorry, not machine readable, most human readable, and the most abstracted away from an actual computer, right? Okay, right below that, we could write something in C or Java or Python or whatever, okay? Maybe bare bones would be in that category, but it would be kind of maybe a little bit lower down, okay? Then there's assembly, and then finally at the very bottom is the machine code, right? The ones and zeros, okay? So how did we translate this assembly, right? Well, how do we translate the English into the assembly and then the assembly into the actual machine code? What did we have to know for this? We had to know the instruction set, okay, which is our table here, okay, that basically says how you have to write everything down, what format it's got to be in. Okay, so in the same way that, remember when with the Turing machines for that simulator, we had to write them in a particular way: state, read symbol, write symbol, direction to move, state to enter, that sort of thing, right? Um, Same thing here, right? There's some organized, systematized way of writing down the instructions, and right here is, okay? So, how did we translate this into the machine code? Well, again, we just used the table. but we had to do that by hand for now. Okay. What I think I mentioned that me and a few students were working on this summer was what's called an assembler that would do this automatically for you. You would type this and click a button, and it would spit out this and a link to the simulator. Actually, they were also working on building their own simulator, which is a little bit of a loftier goal, but yeah. Okay, so does that kind of make sense? All right, so if we go back to the simulator, right, then what's the cycle of how stuff gets executed? Fetch, decode, execute, okay? And the program counter is always going to tell us where in memory is the next instruction that we're going to load. Okay, so it starts at 00 when the machine is about to start running things. On this machine, it always starts at 00. On real computers, it doesn't have to, but on this one, it does. Okay, so if I want to load in the first instruction, that takes 2 bytes worth of memory to encode. So 2101 is the first instruction. Okay, do we remember what 2101 meant? Register 1, right? So we decoded it by saying, okay, this first digit, the 2, is the opcode. That tells us which kind of operation we're doing. Are we taking data and putting it into a register? Are we taking a register's value and storing it out in memory? Are we doing addition? What are we doing, right? Okay, so that nibble, right, because remember, 1 hex character corresponds to a single 4-bit quantity, which we call a nibble, tells us which operation we're doing. And then the other 3 nibbles, okay, are called the operands of it. And they tell us the specifics as to what that operation applies to. Okay, so in this case, I'm going to load the number 1 someplace. Okay, how did I know it was the number 1? Because what are the last 2 nibbles? 0, 1. Okay, so that's the number. And where is it going to go? Register 1, because that's that first operand, right? So if I wanted to load 7 into register A, what would I make the instruction? 2A07, right? Okay, does that make sense? Okay, so we just did the decoding step, which is there, okay? So there it decodes. We're going to take the number 1 and put it into register 1, okay? And then actually do it, that's the execute step, and bam, there it is. Okay, and the whole cycle starts over again. Fetch, 2202. Opcode, 2. Destination register, 2. Value, 02. Okay, so put the number 2 in register 2. That's the decode. Execute, there it is. Okay, then 5312. Opcode, 5, which is, do we remember? It's the one for addition. Okay, and here, what 2 registers am I adding together? Registers 1's contents with register 2's contents. I add them. I get something. And where am I going to put the answer? Register 3. Okay, so that maybe kind of bothers you that the destination is written before the sources. Maybe. It's like that in a lot of assembly languages, right? So the author of the book who came up with this instruction set in the first place, right? He's old and retired now, and was a professor at Marquette in, I think it's Milwaukee. Yeah. Any of you guys heard of that school? Are they like big in basketball or something? It seems like. Huh? Hmm. Well, if they make the March Madness, they must be at least a little bit good, right? Um, you know who else made it to March Madness? Us. Just D3 March Madness, but right? Yeah, it would have been awesome if we had won. That would have been really cool. But because what we lost in the semis, yeah, so we would have gotten annihilated. Yeah. So, um, yeah. Okay. Anyway, so he wasn't making this up in a vacuum, right? He's a computer scientist, right? And so and because he's relatively older, and kind of at the end of his career, right, he would have been active and training in the 70s or whatever um, when and therefore would have been exposed to the machines of that day. Okay, and so what he's made up here is, in some sense, reminiscent of machines of the day. Not perfectly, but that's okay, right? He made it up for teaching use. Okay. Um, okay. So this is going to add register one contents with register two contents to get register three's contents. So we've fetched it, we've decoded it, and then we execute it. And of course, there's the number three. Okay. And then operation three takes a number from a register and sticks it out into a memory address. Okay, so here I have to specify which register and which memory address. Okay, and in this case, because I was the one that wrote this code, I just chose to take register three, that was our sum, right, after we added, and stick it all the way into memory cell FF, which is down here at the bottom right. Okay, nothing special about that address. I just had to put it somewhere. And there it is. And then, of course, we'll get the halt. Okay. Now, the one nice thing about this is you can hit clear and run. It will do it in an automatic fashion. And it takes half a second to execute each of the fetch, decode, execute. So that means that this simulator is operating at a frequency of 2/3 of a hertz, right? 2/3 cycles per second. I think you guys would agree that's pretty slow. It's slow enough, though, that you can watch the execution and keep track of everything that's going on. Okay, even for a relatively complex program. Okay, okay. So let's doctor this up a little bit, and in particular, what would happen if I wanted to change the numbers that I was adding? So I was adding here 1 and 2. Let's say I wanted to add 5 and 7. Just whatever, make something up. What would I need to change? Yeah, I'd have to change some of the pieces of the program. So I'd have to change the O1 and the O2 to be 5 and 7, respectively. Okay, so I can do that, but I've actually changed the program. Yes, because if I do this, oops, if I do that, I've edited my program. Right now, I haven't edited it in any like really glorious way, but I've changed the program. Okay, and now if I run it, we get C as our result, right? Because what's 5 plus 7? 12, but in hex, that's C. Okay. And then it stores that out into memory. Okay, great. Okay, so um, you notice that when I was editing the program, I did show you guys the clip of when we were talking about ASCII. Did I show you guys the clip from The Martian, or did I at least mention it? Okay, so the clip in The Martian, right, where he figures out, okay, he's got the camera from the old rover that he dug up, and NASA can control which way the camera faces. And so if he wants them to send him a message, he put up the stakes that had 0 through F, and then I think he also put like a special one for a question mark, and maybe a period or something. He didn't actually have to do that. 0 through F alone would have sufficed. Okay. Um, and then they would point the camera, and so it would be pointed at like 2, 7. Okay, so he'd write down 2, 7, and then look that up in the ASCII table, and then okay, it's this character, and then he could figure out what they were sent, the message they were sending him, and then he had that whiteboard so he could write and just hold it up, and then they could read from the picture. Okay, okay, so you guys know that scene. Did I play it, or I know I played it for the other class. Did I not play it for you guys? Okay, I did. Okay, excellent. Okay, maybe you weren't there that day. Maybe you were hungover. Um, okay, well, anyway, so the later part of that part clip or whatever is that they send him a set of instructions to edit the code in the rover so that he can just type in the rover and he doesn't have to actually like do the thing with the pictures anymore, right? So that's kind of what we just did here, right? We made some slight tweaks to the code to change what it was. Okay. Now, editing your program code is maybe not ideal, right? Now, for something silly like this, where I'm just adding two numbers, okay, who cares, right? But if I'm imagining that I want to have like a calculator, or maybe like on a real computer, I might want to have the user be able to type in two numbers, okay? Then I don't want to necessarily hard code the fact that it's the number 5 and the number 7. What would be better is to get those things out of memory, and then the user in some other way could put those numbers into memory. Okay, so does that make sense, the idea here? Let's, instead of pre-choosing numbers, let's choose what memory addresses we're going to get them out of. Okay, so that brings us to our next example. Okay, and I need to make some edits to this, of course. Let's see. Load R1 with FD, load R2 with FE, add 3, 1, and 2, store R3 and FF, and then halt. Okay. Okay, so the first instruction here looks very similar to what it was before. Okay, am I going to load the number or FD into register 1? No. Okay, so let's contrast. How does this first instruction differ from this first instruction? Okay, there's two differences. What are they? And just how I typed it. You don't even have to know what it means to identify the two differences. Yes, $ instead of hashtag. And what's the other difference? Instead of 01, what did the other instruction have? FD. Okay. All right. So what's the distinction here between $ and hashtag? Okay. So again, when I was defining this language, I was trying to make it look like other actual assembly languages that exist. Now, there's a huge variety of them, and they all have their own little like idiosyncrasies. Okay, but one of the things that I wanted to do was say, how do you know if I write down the number 01 or FD that I'm talking about the memory address FD or the specific number FD? Because those are two different things, right? One of them is a number on the outside of the mailbox, and the other is the number that's actually in the mailbox. And those could be different quantities, right? Okay, so how do I know if I'm talking about a memory address versus an actual just number? And the scheme I decided to go with was that hashtag means the specific number, and $ means that as a memory address. Okay, so the difference between $01 and hash mark 01 $01 would mean go to memory cell 01 and whatever you find there, load it into the register. Whereas hash mark 01 would mean load the actual number 01 in. Okay, so do you guys see the distinction? It's about mailbox number versus contents of mailbox. Okay, so let's look at, thank you. Thank you, Siri. Okay, so what I've done is I've put the number 1 and 2 down here in cells FD and FE because I'm going to load those numbers out of memory and into registers. Okay, so in terms of the encoding of the instruction, what's changed this time? What's the opcode this time? 1, not 2. Okay, so what's the difference between, what did opcode 2 do? Took a specific number and put it into a register. What is opcode 1 going to do? Loads the contents of a memory address and puts it into a specific register. Which memory address in this case? FD. And which register? Brad? 1. Okay, so what is in memory cell FD? It happens to be the number 01. Okay, so when I execute this instruction, what am I going to see over here in register 1? The number 01. Okay, all right, so let's continue the execution. Let me just automatically run it. Okay, what do we see in the registers? What got loaded into registers 1 and 2? 1 and 2, okay. I'll change those numbers in a minute. What was in register 3? There's some, which happens to be 3. And then where did I take the number 3? I stored it out to memory in FF, okay, which just so happens to be the last memory address, but I had to stick it someplace, so seems like just as good a place as any. Okay, make sense? All right, so does this program functionally do anything different than the last one? It just adds 2 numbers. What's different is where are the numbers to begin with? They're in memory instead of being part of the program's code itself. Okay, so sometimes you do need to hard code numbers. Other times you want them to be things that you could change and rerun the program. So for example, if I changed this to 5 and that to 7, oops, that is not the button I meant to click, sorry guys. Then, and I rerun it, then what's going to end up in memory cell FF when this is all said and done? OC, which of course is 12, okay? All right, does that kind of make sense? So in this case, because I just wanted my program to add 2 numbers that the user chooses, it made more sense to load them from memory. In other cases, it makes more sense to hard code a number. For example, how do you know, well, okay, let's say that you have a program and you have some quantity that you're keeping track of, like a counter, and you need to add 1 to that counter. Well, then you would want to load the number 1 into a register, right? So that you could add 1 to some other quantity. And adding 1 to things, as we've seen, is something we do all the time. Yeah? Okay. So, good? Yes. Where? Say that again. I'm not quite sure I understand the question.
Wasn't the first time that we did all this in memory 00 was 01?
Oh, you mean right here?
Yes.
It was 2-1.
It was 2-1.
Yes, because the first nibble is the operation code, which for the first program was load a specific number. For this program, it's load from memory, right? So the difference between opcode 2 is opcode 2 doesn't touch memory. Opcode 1 does. Okay. And now, how do I know that? Again, we go back to the table, right? We have to, I mean, you guys don't have, you're not going to memorize this table. Okay. And I realize looking at it, I need to make a few modifications to it. But how are you going to know the difference between opcode 1 and 2 unless you have the table? You have no way really of knowing. I mean, you can look at the number 1 and the number 2 and say, yes, those are different, but that doesn't get you anywhere unless you have this table. Okay, so this table here is called the instruction set, and our instruction set is pretty short, right? It has how many instructions? 12, one of which is halt, so that almost doesn't even count. Okay, um, and so it's pretty limited in that sense. Okay, if you look at the manuals for processors of, say, the 1970s, like my old favorite, the 6502, right? It's a few hundred pages. Okay, maybe even less than that because you can condense it somewhat. That's not that bad, right? And heck, that kid's book that I pulled up on Monday, right, basically has most of the stuff there. Um, Now, for a modern processor like what's in the Raspberry Pi or what's in all of your iPhones, the instruction set manual is thousands of pages. Okay, and who's going to actually read and or use all those 1,000 pages? Well, okay, other than people like me, right? The people that work at Apple and ARM and Qualcomm and whatever, and that are actually programming and building these things. Okay.
So, like, they're not reading the entire 1,000 pages, right? They're only probably reading snippets. I know what I'm talking about. It's like in software updates.
Either, yeah. So, really, who's going to be reading that stuff are the people who work on compilers, right? And who maintain compilers, because the compiler has to know the instruction set. Okay. So, they're going to dig through and be like, okay, what do we need to change based on this thing? Um, and so, yeah, it's not as if like every engineer at Apple is going to have a copy of that whole several thousand pages in a big ass binder on their shelf, right? Now, some of them are, but the guys who are making, um, the product images for the website, they don't care. They don't need to care about that. But the people who are in the hardware group and the like operating system low level kind of group, those sorts of people, they really do care about the instruction set, and so they will have those manuals on hand. They need to, or washed out college professors at tiny little dude schools in the middle of a flyover state. Yeah. Okay. Um, right. So not a very long instruction set, and like while I don't expect you guys to memorize this, um, it, it when there's only 12 instructions, you kind of start to learn it by osmosis, and you don't have to keep looking back at the table. So a good example of this would be, in your language classes, let's say you're reading, some snippet of something written in a different language, and you come across a vocabulary word that you don't know what it means. What do? You look it up in a dictionary of some sort, right? Either electronic or dead tree. Well, if you have to look up that word 17 times, what's probably going to eventually happen? You get annoyed with having to look it up, and eventually it just sticks, right? Right. So, point being, right, if you have to keep looking something up, you're human, right? Your brains are designed to notice patterns and to have short and long term memory to preserve that information. You eventually stop having to look it up, right? It's kind of the same thing here. First couple of times you use the table, you're going to be using it religiously. Eventually, you could get to the point where you have it essentially completely memorized and don't need it at all. Okay. Um, but you guys aren't there yet. Okay. So, I mean, it comes with practice, right? how do you learn this instruction set and doing things? You got to write stuff, right? You learn to code by writing code. And maybe that code's crappy. Maybe it doesn't work. And maybe your professor looks at it and says you're an idiot and then points to something and tells you to fix it, right? But that's how you learn any language, right? Is by doing it. Okay. So, of course, what therefore the assignment's going to be for this stuff? F and do it. Okay. All right. So, um, and they'll start small, right? The two programs we just wrote here were only 5 instructions. Okay. And then they could get quite long, like later examples I have in the thing. So I've got a program in there that calculates Fibonacci numbers. I had to make a self-modifying program to do it, which was kind of annoying, but them's the breaks. Okay, now there is one thing that's really important that I want to talk about now, which is I really need to give you 2 versions of this opcode table. Okay, because what I've got here no longer matches 100% what's in the book, and therefore what works on that simulator. Okay, the original design of this processor, opcode 6, did did the arithmetic not as integers but as floating point numbers. Okay, so you guys remember when we talked about floating point numbers, we defined sort of an 8-bit floating point standard, and then we looked at how you could manipulate those or encode or decode or even do some arithmetic with them. Okay, so opcode 6 in the original book's version was not subtraction, it was addition of floating point numbers. Okay, um, I decided to change that for the simulator that my guys are building and changing the language a little bit for 2 reasons. One, the way that the book actually defines the floating point standard um, is not compliant with IEEE 754. Okay, so how did we define our floating point standard? How many sign bits were there? 1, it's a sign bit. How many exponent bits were there? 3 with a bias of 3. And how many mantissa bits were there? 4. Okay. But remember we talked about the hidden 1? Okay. So, yeah. So what was the hidden 1? Well, when you write a number in scientific notation, you want to write it as 1 point something times 2 to the something. Do you have to specify the 1 that's before the radix? Why not? Why do you not have to in binary? Because it can't be 0, and so what's left is as the choice. It must be a 1. Okay, this is a trick we cannot do in base 10, because how do you know it's 6.02 versus 9.02? You don't, right? You have to specify that digit. But in binary, you don't have to specify that digit or bit. Okay, so in the book for the floating point stuff, he never talks about the hidden 1. Okay. Now I know why he did it, because when I first did the hidden 1 with you guys, you were like, "Wait a minute, this is whack." Yeah. You guys agree? This is confusing. And after working with it and talking about it, you guys saw the logic of it and realized that it really wasn't that horrible. Yeah. Okay. So he chose not to talk about the hidden 1 to simplify what was in that section of the book. Right. I get it. I really do get it. Okay. But and when I first taught the floating point, I actually just did it the way he did. And then I came to realize the error of my ways when I was like, okay, well, now let me look at the 32-bit version, because I was teaching CS241. And I was like, okay, this is stupid. I'm not going to define something that doesn't scale up in later classes. That's silly. Okay, so I've decided to change the architecture a little bit and make opcode 6 the subtraction opcode, which was missing in his original. Okay, now what I want to convince you of today and Friday, we'll obviously have to keep going with this, is that I don't actually need the subtraction opcode. Okay, but having it will make for convenience. Okay, and so I want to convince you that programmatically it is possible for us to do subtraction without making use of the subtraction opcode. Okay, now the last thing about this is if you use opcode 6 on that online simulator, it's going to do addition of floats because the guy who programmed it, Joel, nice guy, we've corresponded by email. He thinks it's great that we're using. He did that simulator as a class project for his master's degree, I think, and thinks it's really awesome that we're using it for class. Okay, so anyway, if you use opcode 6 on his simulator, it's not going to work right. And where it will work right is once Owen and John and I get our simulator fully running. Now, that may not happen by the end of the semester, so c'est la vie. But yeah, this is a work in progress. Okay. Yeah? Okay, so let me switch over to the iPad, and I want to convince you that we can do subtraction without doing subtraction. And you already know the answer. Or you ought to already know the answer. Okay, so let me just take two numbers. Okay, answer. We know the answer. We're not idiots. Okay, but how would I actually do this computation if I can't do subtraction? Yes. Decrementing? Okay, but that's subtraction in some sense. Okay. Um, but I can do something else. I want to think of A minus B as being A plus negative B. Okay, so I'm going to be sneaky with a set of parentheses. Okay, if B is in hex this, or in binary that, what is negative B? Yes, it is 0xFF. How did you get that? You remembered. Okay. So how did we get the negative of a number if it was written in binary? You flip the bits and you add 1. Well, we can definitely add 1, right? Exactly. Okay. So how did I get that? I flipped the bits. That's one too many. I added 1 and I got that, which is FF in hex and represents -1 as a signed 8-bit integer. Okay, so you guys remember us doing that? Okay, now, do we have an operation that's capable of doing addition to add 1 to a given binary number on our machine? Yeah, we totally have that. But we need an operation that can do this bit flipping for us. Okay, and I claim we have that. Okay, and Thomas just said it. What operation is it? Exclusive OR. Okay, but if I'm going to use exclusive OR, I really need two numbers. I have this number, the number that I want to flip everybody, and I need to XOR it with some other bit pattern. Okay, and Thomas also said it. What bit pattern? All ones. Okay, so let me convince you that that's the correct choice. Okay, so let's remind ourselves, what is the truth table for XOR? It's this, right? Okay, so what's the difference between XOR and inclusive OR? What was our cheesy dinner food related example? You can't have both pies, right? But you could be in both math and computer science, right? But if you're going to go to a restaurant and you order dessert and your mom's buying and you're like, I'd like the turtle cheesecake and the creme brulee, you're going to get neither. And she might leave your butt there and say that you're doing dishes to pay for your dinner. Okay. That was always the threat when I was a kid. I don't know how many. Did anybody of your parents ever threaten to make you go back in the kitchen and do dishes to pay off your? No. Okay. Well, I don't know. Maybe parents in the 80s and 90s had different parenting techniques. I'll give you another one. This one actually might horrify you guys. So when you were little, okay, and you were going to the store with one of your parents, and you were crossing the street or something, what would they make you do? Hold their hand so that you don't get run over or something. Okay. How would they explain why you should hold their hand? Did they ever do that? Or did they just say, hold my hand and do it? Okay.
So you don't get hit by a car.
Okay. So my mother told us of the legend of greasy spots. Okay. So imagine the Walmart parking lot. It's full of oil stains and all kinds of stuff along the concrete, right? Those are greasy spots. And those are the remnants of children who failed to hold their mother's hands while walking into the store. And that there were like, I always imagined these as like Corvettes that were like stationed all around the parking lot, right? Just looking and watching. Oh, there's a kid not holding his mom's hand, and it'd start to rev the engine, right? And then, off they go, right? So this was the story my mother told us when we were kids. Um, and well, I'm here to, it works, right? So I can't argue with the method, but yeah, okay. So why is exclusive or the right choice here? Well, when I flip the bits, I want to turn ones into zeros and zeros into ones. Okay. So if I XOR a bit, if I XOR it against a zero, what is 0 XOR 1? 1. What's 1 XOR 1? 0. That flipped the bit. Yeah? Okay, so if I want to flip a given bit pattern, let's take in our case, we had the bit pattern this. I'm going to write down the number, all ones, and I'm going to XOR it with that thing. Okay, now, when you do a logical operation, you're doing it bitwise. Okay, so addition, you know how you have to carry and stuff, right? There's no carrying with XOR. Okay, you just do it first bit with first bit, second bit with second bit, third bit with third bit, and so on. Okay, so if the bit on the top number is a 1 and I XOR it against a 1, what am I going to get? And then what am I going to get for all the other 7 bits? Which is exactly the flipped version. Okay, brilliant. You know, like those Guinness commercials, right? No? Okay, so we go back to our instruction set and look what we just so happen to have. We have the ability in our machine to do a bitwise XOR. Okay, now, in a circuit sense, how do you do bitwise XOR with two 8-bit numbers? What do you need? You need 8 XOR gates, right? Well, fortunately, you guys all built me a bunch of XOR gates, right? We know how to build an XOR gate, And if I can do it once, I can do it 8 times. Right? It's almost like this stuff is coming full circle. Yeah? Okay. All right. So this begs the question, though. We know the steps. We've got the instructions to be able to do it. Now we just need to actually put it together and write the code. And that, I think, is where we will start on Friday. I'm going to stop the stream because I have one other thing to say.